Well, hello everyone, and thank you for joining us for another lecture for Introduction to Computer Graphics. Today, our topic is, drumroll, ray tracing. Yeah, so we started talking about different rendering algorithms. We landed on ray tracing. So we're going to spend some time on ray tracing today and next time as well. So we're gonna finish up our discussion on rendering by talking about all sorts of stuff that is sort of related to ray tracing. So today I'm saying the topic is ray tracing, but mostly we're going to be talking about ray intersections. I'm also going to talk about other stuff that's related to ray tracing. That's our topic. All right, so let's start with remembering. Remember this? What we're trying to do is that we're trying to render an image using a camera that we're seeing through this screen, and we have a whole bunch of triangles in the scene, and we're going to be using ray tracing to render that image. All right. So for any point on the screen, we're going to be generating a ray that originates from the camera and goes through that point, and then we're going to trace that ray and find out which of our scene primitives it hits, if anything. And if it hits anything, then we're going to shade that point, and we're going to set the color of that pixel to that point, and we'll be done, right? So that's ray tracing in a nutshell, and that's what we're going to be doing. But let's start with a ray. So what's a ray? A ray is a point or an origin. So it has a position. Let's call it an origin of the ray, and it also has a direction. So a ray is defined by a point and a direction for the purpose of computer graphics. A ray, mathematically speaking, is just going to be half a line, right? So in that sense, you can think of this as the structure that defines this half a line, right? So it starts at this position and it goes in this direction, right? So half a line, this half, mathematically speaking. You can think of this as a position and a direction, and that position and direction sort of defines this whole half line over here, right? For any point on this ray, let's call it x. We can write x as a combination of this position and direction, right? So starting from this position, starting from this position P, if I go along the direction of D enough, I can reach this point X, right? So if I were to write this position X as a combination of these two, I'd say I start with this position P, that's the ray origin, and I travel along direction D by a magnitude of T. T is just some scalar value that tells me how far I need to go from P to reach X. So oftentimes people think about this T as the distance between this position P and this position X, right? And it can be the distance only if this D is a unit vector. If it's a unit vector, then T is the distance, right? If D is not a unit vector, that T just tells me how many multiples of D I have to go to reach X starting from point B. When T is positive, we're going to be on this side of the ray. I would say we're going to be in front of the ray, all right, in this side of the ray. So we're going to be on the mathematical ray. Actually, I believe mathematical ray also includes the point where T is equal to 0. So at this point, where T is equal to 0, this term cancels out, so we're left with P. We're going to be exactly at the ray origin. And if T is negative, then we're going to be on the backside of the ray. I often refer to this as we're going to be behind the ray, right? So X is going to be sort of behind the ray on the backside of the ray if T is negative. But oftentimes when we're doing ray tracing, we're going to be interested in positions that are going to be in front of the ray. They're going to be represented with T values that will be positive. Not even 0. oftentimes we're not interested in things that are at t is equal to 0, because if I have this ray, I'm at this position anyway. I will be interested in stuff that is in that direction, but not exactly at this point, right? So we're going to be interested in stuff that's going to be t greater than 0. All right. So what am I going to do with this ray? I have this ray. What am I going to do with it? I'm going to take this ray, and I'm going to see if this ray, let's say this ray that I generated from my camera going through a sample on my screen, I'm going to check if this ray intersects with any of the objects in my scene, right? That's what I'm going to use this ray for. So the next thing to look at, of course, now that we have a proper definition of what a ray is, the next thing to look at is to see how we can compute intersections of this ray with our scene objects, right? So ray intersections. Let's start with the simplest thing. Like, we're going to be intersecting this ray with, let's say, surfaces, right? Remember when we talked about surfaces, one of the first things that we mentioned was implicit surfaces, right? So let's start with the definition of implicit surfaces and how we can handle implicit surfaces using ray tracing. Implicit surfaces are not easy to render using rasterization, right? With rasterization, we were taking triangles, we were projecting triangles. But if I have an implicit surface that is defined by a function like this, rasterizing this is very, very hard. Actually, I don't even know if it's possible. Like, in some specific cases, we might be able to do that, but in general, no. That's one of the reasons why our rasterizers that run on our GPUs will be just rendering triangles, right? But with ray tracing, we can actually easily handle implicit surfaces. So all I got to do is to make sure that a point on the ray can be represented using this function. So if there exists a point on the ray that satisfies this function, that satisfies the definition of an implicit surface, then that point on the ray is also a point on the surface. That means my ray intersects with that implicit surface, right? So that's all I got to do is to write this equation, that's a point on the ray, and check if these two equations can be satisfied. That is, if I take this x and replace it with this form, that is, if I can write this, that means that my ray intersects with this implicit surface. That is, if there exists any t value, such that this equation is satisfied, that means that my ray is intersecting with the implicit surface. That means it's a hit. Okay? But if this equation is not satisfied, if it's always non-zero, for all possible t values, if that is the case, then I'm going to say that no, that there's no hit. That means that my ray is not intersecting with the implicit surface. Simple enough? Right, so you can literally take any implicit surface definition and use this approach to find ray intersections with the implicit surface. Although implicit surfaces can have quite complicated functions here, so figuring this out, as simple as it might seem, can be a little bit tricky. So let's see an example of this with a relatively simple implicit surface definition that is actually used quite often with ray tracing. That is going to be an implicit sphere. So let's take a look at ray-sphere intersection using implicit definition of a sphere. All right. So an implicit sphere, of course, has this function. So what's the function for an implicit sphere? What's the sphere function? You must have seen this a million times. We have even talked about this earlier, like x squared plus y squared plus z squared minus r squared is equal to 0. That's the sphere equation, right? But I like the vector form. I like the vector form of this equation. I like writing it like this, that x dot product with itself, x being a vector, dot product with itself minus r squared is equal to 0. I find it more intuitive. But this is specifically a sphere that is at the origin, right? If the sphere is not at the origin, that is, if its center position is not the origin of my coordinate frame, then this equation will turn into this equation, right? This is the sphere equation that I like looking at. So I like this because like any position x on this sphere will of course satisfy this equation. But I like writing it this way because I find it quite intuitive. And if this doesn't look intuitive to you, let me make this intuitive for you, right? So I would like you all to like vector equations, because if you write things in vector form, and if you understand those vector forms, you'll see that they are a lot more intuitive than the scalar equations written for 3D objects. So for this equation, any position x satisfies this equation, right? So what is a position x? Position x, you can think of this as a vector from the origin towards a point on the surface, right? So what is this vector? From the origin to a point x on the sphere, it's x minus c. Right? Simple enough? Good. So, tell me, what is the definition of a sphere? A sphere is a collection of points that are equal distance away from the origin, right? Just a collection of points that are equal distance away from the origin. So, any vector starts from the origin, goes to a point on the surface. Any vector should have a constant length. That length is the radius of the sphere, right? So I can write a sphere like this, right? This, whatever this vector is, so x is a position on the sphere minus the origin. The length of this vector has to be a constant. That's the radius of the sphere, right? Simple enough? So what is this? Length of a vector? Length of a vector, by definition, is the dot product of that vector with itself, square root. Right? So this is the length of a vector. That's the definition of a length of a vector. And this, if I take the square of both sides, I'm going to get this, right? Dot product of a vector by itself is equal to r squared. Well, guess what? It is exactly this equation. So this is what this equation says, nothing else. So if you really understand what this equation says, it's really, really intuitive, right? That's why I like vector equations. Also, they are a lot more compact than the scalar forms. So okay, let's put all this stuff away. We're going to talk about ray intersections with a sphere, right? So let's say that I have a ray, and that ray goes through a point on the sphere. I'm going to call that point x. And I would like to be able to find that point x. And I would like to be able to check if this ray intersects with the sphere at all, right? So the equation, the parametric equation for x, any point x along this ray, I can write it like this, right? We talked about this. X is equal to p plus some t times d, right? So that's for any point along this ray. So if I take this and put it up here and replace all x's with p plus td, I am going to get this equation. Simple enough? All right, so next step, what I'm going to do is I'm going to take these components with t and move them to the side. I'm just moving them around, nothing else. And if you expand this, if you do this dot product, component by component dot product multiplication, if you expand this, you get this equation. All right. So what do we see here? In terms of t, I see at the all the way here, there's a t squared term, there's a t term, and there is a constant term. So this looks like a polynomial of t, a polynomial of degree 2. So this is a quadratic polynomial of t, right? So what does that mean? A quadratic polynomial, you must have seen this in the when you're investigating quadratic polynomials in math classes. A quadratic polynomial is equal to 0. So this is going to have at most 2 roots, right? So there's going to be 2 different t values, 2 different values for t that might satisfy this equation. So maybe there's going to be no roots, that no t-value satisfies this. In this case, that will mean that our ray does not intersect with the sphere. Or there might be up to 2 different t-values that will satisfy this equation. And if you look at this geometrically, it makes perfect sense, because if I have a ray that goes through a sphere, the ray will go into the sphere from this point, and it will come out of the sphere from the other end, right? So there's going to be another t-value where this ray is going to come out that will correspond to another point. So what does that mean if I have a single value? If I have a single root, that would mean that these two x and x prime points, that's actually one point. That means my ray is tangent to the sphere. That's what it means. Okay? So it makes perfect sense that we are getting a quadratic polynomial here as our solution, because there are 2 roots. So we should expect to get a quadratic polynomial for a sphere because of that, because there are 2 roots. And we did, so everything is good. So let's simplify the notation of this just a little bit. So I'm going to call this term A. It's just a scalar, right? Dot product of D by itself. It's going to give me a scalar value. I'm going to call that A. I have another dot product here, 2D P minus C. I'm going to call that scalar value B. And the remaining scalar value, that's also another scalar value, that I'm going to call it C. So it goes into this very, very familiar form for a quadratic polynomial. AT squared plus BT plus C is equal to 0. So what's the solution for T? Most of you should know this by heart by now. That's the typical quadratic formula. That's minus B plus minus square root of some delta, with 2 divided by 2a, and delta is equal to b squared minus 4ac, right? So this is the standard quadratic formula. This is the solution of any quadratic equation, and we can easily use this to solve our problem. So what this is going to do is it's going to give us the t values where our ray will be intersecting the sphere. And if I know the t values, I can find x, right? If I know t, I already have my ray formulation. I already know my ray origin and ray direction. So I can easily compute the position x that's on this sphere surface. So that's all I need to know. I just need to know the t value. So, but here's the thing. My ray may or may not intersect with the sphere. How would I know if the ray intersects with the sphere? I will know by looking at this delta, right? So delta here has to be positive or 0. It cannot be negative for us to have a real root. If delta is negative, then I'm going to have an imaginary root. But in this particular problem, I don't care about imaginary numbers. All I care about is real values for t. Imaginary values of t, I have no idea what that means geometrically. So I don't care about that. So if delta is negative, I don't have a root. I don't have a real root anyway. So that means my ray is not intersecting with the sphere. So if delta is negative, I am going to say that there's no hit, right? There's no real value of t where this ray is going to intersect with the sphere. That means I could not find a real solution for this equation. If delta is equal to 0 or a positive value, then I will say that I found a hit. Then I know that my ray intersects with the sphere. And depending on the value of delta, I may have 1 or 2 intersections, right? So depending on the delta, I can say that my ray intersects with either one point that's going to be tangent to the sphere, or the ray goes through the sphere. That means there's going to be 2 roots. But there are 2 solutions, right? Now I need to figure out which is the one that I want. This is plus minus. Which one do I pick? Actually, in this case, the answer is quite easy. In this case, I will always want to pick the one with negative here. The reason for that is, if I look at the other one, the other intersection, x prime, that is going to always have this positive version. And why is that? Now, the closest hit point, the one that's closer to the ray origin, is going to have a smaller t value, right? A smaller t value. If you look at these two equations, the only difference is the sign over here, this minus and this is plus, obviously. And I know that square root of delta, which is a positive value, this is a positive number. And a is also positive. You know, what is a? A is this guy, right? This guy. That is the dot product of d with itself. That means it's the length of d squared. The square of the length of d. Well, the length of d is obviously positive. Square of its length, well, square of any number is positive. So that's definitely positive. In fact, in most cases, this d is going to be a unit vector. And if it's a unit vector, its length is 1. So square of its length is 1. So a is, in most cases, going to be 1. So this is going to give me a smaller t value than this one. So this is going to give me a larger t value. This is going to give me a smaller t value. So if my ray origin is outside of the sphere, then this one with minus is going to give me the very first hit, the very first intersection of the ray with the sphere. And this one is going to give me the next intersection, right? And if I'm rendering a sphere and I want to see what's outside of the sphere surface, then I will always be using this one. Always be using this one. I will never be using this one. Except if my ray origin is inside the sphere, and I want to see what is inside the sphere surface. I'm inside the sphere surface. I'm inside the sphere, and I'm looking at the sphere surface from the inside, and I want to see the inside part of the sphere surface. In that case, I'm going to be using this guy, right? But for most applications, I won't care about that part. I will only care about the outside surface of the sphere. So I will be using this one. Let me answer before you ask. For the project, we will be interested in the outside of spheres, and we will be using this one for the upcoming ray tracing project. All right. So yeah, that's about it. This is the entire sphere intersection. It's just an implicit surface. We took the definition of a ray, and we put it inside the sphere equation. Then we did the math, and we figured out where the roots were, and we found out which root we're interested in. And there it is. And if I know t, then I can compute this point x easily. And I can compute the surface normal at that point x, right? At the surface normal at that point x is going to be in the same direction as x minus c, right? The vector from the center to the point x on the surface is going to be my surface normal vector for the sphere. So I'm all done. I found the position. I found t. That means I found x. That means I could compute the surface normal, and I have everything I need to start doing my shading, right? Most probably for most applications anyway. I haven't told you how to compute the texture coordinates, but it's a whole other thing. That depends on how you're mapping the texture, so don't worry about that. All right, so this is ray sphere intersections. Simple enough, not too hard, right? Let's take a look at one more thing before we continue. Let's take a look at another implicit surface. That's going to be a simple implicit surface. It's going to be the ray plane intersection. So in this case, I have a plane that's defined by this normal. So does anybody remember the vector equation for a plane? It's going to be this guy. The implicit equation for a plane is going to be x dot product by n minus c is going to be 0. So that's the implicit equation for any plane, any infinite plane. And what I'm interested in is finding the intersection of a ray, computing the intersection of a ray with this plane, and finding where this ray intersects with the plane. Right? So we're going to do the exact same trick. So my ray equation, parametric ray equation, any points x along the ray defined by p plus td. I'm just going to take this, I'm going to put it inside the implicit equation for a plane, and that gives me this formula, right? And here, t is the only unknown. I know everything else. I know p, I know d, I know n, I know c, I know everything else. I just don't know t. And as you can see in this case, this is a linear equation, right? There's nothing complicated here. I don't need a quadratic formula even. This is linear, and if you just move things around with some very simple algebra, you can actually find that t is supposed to be this. Right? Simple enough? Alright, there's one caveat here. There's one little thing that you kind of need to be careful about. How do I know whether or not my ray intersects with this plane? Right. So it seems like this always intersects, right? There's always a solution. There isn't always a solution. There's a very specific case where the ray will not be intersecting. That's right. The ray will not be intersecting with the plane. That is when this denominator is 0. Right? If this is 0, then t is going to be infinity. Right? So that's not going to fly. Yeah, that means my ray is not intersecting with the plane. So what do I do? What does that mean? D and n, if I take the dot product and that's 0, that means these two vectors are perpendicular to each other, right? So that means that I have a ray that is perpendicular to the plane normal. Its direction is perpendicular to the plane normal. So this ray will not be intersecting with the plane, right? And if that is not the case, I just need to check that special case. If that's not the case, I'm going to say, yes, it intersects. It intersects with the plane, and at this t value, whatever that t value is, right? Simple enough? Very, very simple, right? It's a lot simpler than, it is simpler than the sphere equation. Maybe not a lot simpler. The sphere equation was relatively simple as well. So, but this is even linear. I only have one root. And that makes perfect sense because a ray cannot intersect with a plane more than once, right? It makes no sense. So geometrically, it makes no sense. So it's perfectly understandable that I'm getting a linear equation here, and I'm getting a single root for t. Good. All right. Actually, there's something a little bit simpler than this even. That is, if this plane is not just an arbitrary plane, but it is an axis-aligned plane. If this is an axis-aligned plane, that means my surface normal here, my plane normal, is either x direction, y direction, or z direction, or negative x, negative y, negative z, right? So let's say that it is z. So let's say that this is my plane normal, 0, 0, 1. And c can be any value. I don't care about c. It just means, it's just going to determine where the plane is, its altitude, if you will, and the n is my surface normal. So what happens in this case? In this case, the dot product simplifies a little bit, right? Because I have 0, 0, 1. So this dot product of p dot n will give me just the z component of p. And this is going to give me just the z component of d. Right? So it's going to be just this. Fairly simple. Now, I want to just spend a minute here just talk about what this means geometrically. What's the meaning of this? Now, if I'm interested in the z component of D, it is this magnitude here. Like if I just take the z component of D, it is this vector, right? This kind of small vector, this big. And c minus pz is going to give me where this plane is in the z coordinate and where this point is, and the difference between the two is going to give me this length. So this whole length divided by this length is going to tell me how many times of this length I need to go until I go from this point all the way down to the plane, right? So I'm just dividing it by that magnitude, and of course that's going to give me the t value. So that's the geometric interpretation of what's going on here. All right, so planes, infinite planes and spheres are two of the very few implicit surfaces that are commonly used with ray tracing, because they're very, very useful, and they're also fairly easy to handle with ray tracing. They are used in practice. But the most common primitive that we will be using for rendering, with or without ray tracing, is going to be triangles, right? So the more interesting bit here is, how do you compute intersections of triangles with rays? Because that's going to be the main operation that we will be using when we're rendering triangular meshes. And since we're representing most objects using triangular meshes, this is the operation that we will be doing very, very often in a ray tracer. This is a very old problem. It's been around as long as ray tracing has been around. Back in the 80s, when people were very much interested in ray tracing, this operation was expensive. Just doing this was very expensive, computationally expensive. And you're doing a lot of this too. I have a lot of triangles in my scene. I need to check intersections of rays with my triangles. So I'm doing this operation a lot of times when I'm rendering. So this is an operation that I really, really, really needed to optimize. That's why people looked into this a lot, and they figured out actually many ways of computing this, and many optimized ways of computing this. And I have no intention of going through all of them. But I'm just going to give you the intuition of how this works. Just one way of how you could compute this. But I want to give you this disclaimer that there are many ways of computing this, and with different advantages and disadvantages. One of the most popular ones use this idea. So if I have a triangle, using these three vertices of that triangle in space, these three vertices will define a plane, right? So what I can do is I can compute the intersection of this ray with the plane that is defined by these three vertices, right? And if I know how to do this, right? We just talked about this. All I need to know is the normal of this triangle, and I can compute the normal of a triangle by take two edges, do a cross product, that will give you the normal direction, right? And I can fit it in the plane equation to get the constant c, so I can easily build the plane equation, the implicit plane equation, from three vertex positions of a given triangle. And if I have the plane equation, then I can easily do the ray plane intersection, and I find out where the hit point is. But that doesn't tell me that my ray intersects with the triangle. It only tells me that where the ray intersects with the plane, with the infinite plane. After that, I need to check whether that intersection point x here is inside that triangle. That's all I need to check. And one way of doing this is computing the barycentric coordinates of x inside that plane. So it turns into a 2D problem now, because now we're on this plane, so you can convert this into a 2D problem and you can look at it as a 2D problem. And in that 2D problem, I have a point on this plane, and I'm checking whether or not that point is inside the triangle. And for any point on this plane, I can compute the barycentric coordinates. We talked about barycentric coordinates. We talked about how they correspond to the areas defined by different sub-triangles. Using those areas, that's one way of computing the barycentric coordinates. I can compute the barycentric coordinates, and then by looking at the barycentric coordinates, I can tell whether or not the point is inside the triangle. Because if any of the barycentric coordinates components, if any of them are outside of the range 0 and 1, that means my point is going to be outside of the triangle. If all of them are between 0 and 1, that means my point is inside the triangle. Right? So that's one way of doing ray triangle intersection, and it's a very, very common way of doing ray triangle intersection. There are different variants of this. As I said, people try to optimize this quite a bit over the years. I believe the most optimal version includes only one division operation, because division is more expensive than other operations. Especially back in the day, it was considerably expensive. It moves that division all the way to the end of ray triangle intersection, and you have to do the division only if you know that the triangle intersected with the ray, just to find the intersection position and its barycentric coordinates. Anyhow, that's one way of doing, one actually quite popular way of doing ray triangle intersection. I'm skipping the mathy details over here, because I don't think that those mathy details are that important. I just want you to understand the general idea of how you would approach a problem like this, right? And the way you do that is find the intersection with the plane, and then check if that intersection is inside the triangle. Right? That's all I want you to get out of this entire discussion. All right, so that's the ray triangle intersection, and if I can do a ray triangle intersection, since I'm representing anything as triangles, I can render anything. Right? All right, let's see how we do that. All right, we're doing ray tracing. I have a camera. There's an image that I want to generate. So what do I do with ray tracing? For each pixel sample, let's say this guy, for each pixel sample, I am going to be generating a ray, and then I'm going to be tracing that ray. So let's not call it a pixel sample. Let's call it a ray, right? Because that pixel sample will define a ray, this ray specifically. So let's call it a ray. For each ray, I'm going to find the closest primitive, right? So how am I going to do that? I'm going to look at my scene. I'm going to find the hit points. But the important thing here is that I need to find the closest one. All right, that's the important bit here. And once I find the closest one, in this case, it's going to be this red sphere. Once I find the closest one, I'm going to shade that closest one, and that's how I can find the color that corresponds to this pixel. All right, so for each ray, find the closest primitive. Okay, this is a little, how am I going to do that? Well, the simplest thing you can do is just look at all primitives and see which ones intersect with the ray, right? So just find the closest primitive. I can convert it to a for loop, right? For each primitive, what am I going to do? For each primitive, I'm going to check if the ray intersects with the primitive. For each primitive, if the ray intersects with the primitive, I also need to make sure that it is the closest one. Because I'm going to look at all of these, right? I'm going to look at all of them. And then I also need to check, okay, if I found a hit, is this the closest hit? Because I might be looking at these spheres in any order. I don't know what order I'm going to be looking at it in this for loop. So I need to do this loop and look at all the primitives. And for each one that intersects with my ray, I'm going to check if it is the closest hit. And if it is the closest hit, I'm going to record it and keep it somewhere. I'm going to keep looking at all the other primitives. And only after this loop is completed, that's when I know that, yes, I found the closest hit. Now that I found the closest hit, now I can shade it. All right? So that's how this is going to work. I'm repeating this and I'm explaining this sort of slowly because this is exactly what we are going to be implementing for our upcoming projects. Right? So I know this may sound trivial to some of you now that I've explained it, but I'm going to repeat it again because this is what you will be implementing. So here's what we're doing. For each ray, and for a given ray, let's say, I'm going to be looking at each and every one of my primitives. In the project, that's going to be a set of spheres. I'm going to be looking at each one of my primitives. And then, if the ray intersects with that primitive, I'm going to check if it is the closest hit, or if one of the earlier primitives had a closer hit. If it had a closer hit, I don't care. If it is the closest hits so far, I'm going to keep a record of this. And when I'm done, when I'm done looking at all of the primitives, that's when I know that I found the closest hits. And that's when I'm ready to shade. So when you find the closest primitive, you need to take a note of what that is. I need to know what that point is and what the surface normal at that point is and all those details. Everything that I will need to be able to shade that point, that's what I'm going to be saving. Okay, now in this example I have two spheres, fairly simple, right? For the projects, we're not going to have too many spheres. That's going to be fine too. But in general, I might have quite a lot of primitives. Is there a faster way of doing this? Yes, there is, because we need a faster way, because in a scene, I'm not going to have just two spheres, or just two objects, just two primitives. In a typical scene, I'm going to have millions and millions of primitives. Right? And imagine in production scenes, even in scenes that are used for video games and for real-time rendering on the GPU, you'll have a ton of triangles, right? So if I were to do this for loop in this brute force manner, look at each and every primitive, and I do that for every ray, how many rays do I have? Even like one of the lowest resolution screens that we use today, let's say it's 1080p. In 1080p, you have more than 1 million pixels, right? And in 4K, you'll have a lot more. So you have so many rays, you have millions of rays, and you have millions of primitives. Million times million was what this thing looks like. This is not going to finish anytime soon. This is going to be massively slow. This brute force way of doing ray tracing is going to be massively slow. So no, we cannot do that, and that's what we're not doing this. We're doing things that are better than this. That's going to be about ray tracing acceleration. It's a very, very important topic for ray tracing. This is how we have ray tracing that actually runs in reasonable time. And we're going to call these acceleration structures or space partitioning structures because they will be working with partitioning the space. Let's talk about those. So here's my problem. I have a scene with a bunch of spheres, more than one. All right. I didn't have the patience to actually draw 1 million spheres here, but just imagine that this is a very large number. I know this is not a very large number, but let's use your imagination that this is a very large number, a lot of spheres. Now, here's the thing. If I want to do this brute force computation, that I want to check the intersection of my ray with all of these spheres, that is going to take a long time. But if I know where these spheres are, maybe I can take a shortcut. For example, if I know that these spheres just fit in a box, I put all the spheres in a box, or actually I built a box that will contain all of my spheres. If my ray does not intersect with the box, it cannot possibly intersect with any of the spheres, right? I mean, all my spheres are contained inside this box. So if the ray does not intersect the box, then it is not going to intersect with any of my spheres. So, and this is the kind of shortcut that we're going to be using for accelerating ray tracing. And the kind of box that I would like to use is a special box that is going to be an axis-aligned bounding box. A bounding box meaning that it is bounding everything in the scene. And it is axis-aligned, that is, each one of these 6 planes that form the ends of my box, they are going to be axis-aligned planes, right? And there's a good reason for using axis-aligned planes for defining this axis-aligned bounding box. Because we just talked about this a few minutes ago, I can easily do a ray-plane intersection, but if my plane is an axis-aligned plane, then ray-plane intersection simplifies quite a bit. And an axis-aligned bounding box is just 6 plane intersections. So computing the ray intersections with an axis-aligned bounding box is just going to be 6 plane intersections. I'm skipping the details of exactly how to do this because that's the whole point that I would like you to get. The difficult part is just doing the 6 plane intersections, and then you sort of sort all the t values that you get and you figure out whether or not ray intersects with the bounding box. It's fairly easy to do after you do the ray plane intersections. So with 6 axis-aligned plane intersections, which is actually very cheap, right? We talked about this. It's very simple. Axis-aligned plane intersection is very simple. So this axis-aligned bounding box intersection with a ray is a very fast operation, very cheap operation. And I can fit millions of spheres inside this bounding box, and that simplifies my ray intersections with my scene that contains millions of spheres. Only if the ray does not intersect with the box. Right? If the ray intersects with the box, then I'm in trouble. Okay, maybe it wasn't a great idea to put all of my spheres into one box, right? Maybe that was not the best idea. I have millions of spheres or millions of primitives, and I dumped them all inside one box. That was not the best idea. So how about we put some spheres in one bounding box and the rest of the spheres in another bounding box. So I can just do 2 box intersections instead of 1 box intersection. Still, it's relatively cheap if there's just box intersections. And I have, fewer spheres per box, so it's even sort of better. Actually, even better than that, I can take these 2 boxes and I can put them inside a larger bounding box that contains both of them. What about boxes in boxes? That's exactly what it is. So I can just have a box here that contains everything. And if my ray intersects with this box, that's when I'm going to go in and check the smaller boxes. Right? So that brings us to a very, very popular acceleration structure used for ray tracing today. That is bounding volume hierarchy. Bounding volume hierarchy is just a hierarchy of axis-aligned bounding boxes, BBH. There are other acceleration structures used in ray tracing which were very, very popular in the past, but today, when we think about ray tracing, almost always we use some form of BBH. There are different versions of BBH, so that's by far the most popular acceleration structure that we use today. With the bounding volume hierarchy, what we have is a box that contains my entire scene, everything. I just put my millions of primitives inside this box, everything lives inside there. And if my ray does not intersect with it, that means it doesn't intersect with anything in my scene. I can just throw away that ray, go to the next ray, very cheap, very fast, I'm done. If the ray intersects with it, then I'm going to look at the boxes inside this box, right? So the boxes inside this box, I'm going to check both of them. If it doesn't intersect with, let's say, the blue one's gone. I don't have to look at the blue one ever again. If it doesn't intersect with the green one either, then I'm done. But if it intersects with one of them or both of them, it might. Then I'm going to have to go in and look at the boxes inside them, right? And then I'm going to be looking at those boxes, and this can go down as far down as it needs to. And in the end, this is going to define what it looks like a binary tree. To be fair, this doesn't have to be a binary tree, but it forms a tree structure like this. Oftentimes, when people say BVH, they mean the BVH that forms a binary tree, but it doesn't have to be a binary tree. There are cases where we use trees that are not binary trees like this. That is, trees that have more than 2 nodes. That is, boxes that contain more than 2 boxes inside. But anyhow, this is the general structure of a BVH. It's just a tree structure. Most acceleration structures actually are going to be some sort of tree structures. We're going to be traversing some sort of tree, and BVH is today the most popular acceleration structure we use for ray tracing. Just to reiterate, the way this is going to work is that if I have a ray, I'm first going to check if the ray intersects with this root bounding box. If it does, then I'm going to check its 2 child nodes. If it intersects with one of them, then I'm going to go down and check its child node, all the way down to a leaf node. That leaf node is going to contain the original primitives, whatever my primitives are. If there are spheres, it's going to contain spheres. If there are a bunch of triangles, it's going to contain a bunch of triangles, right? And if I have a single object that has a million triangles in it, I'm just going to take that single object, I'm going to split it into pieces like this, such that each one of my leaf bounding boxes, leaf level at the very bottom, leaf level bounding boxes will contain about a handful of triangles only. How do you decide how to group them? Is there a strategy? I am not going to talk about this. That's a big topic, actually. There are good ways of building the structure. There are bad ways of building the structure. If you build this in a very, very bad way, actually, your acceleration structure will still probably help a little bit, but it's not going to help as much. But if you build this structure carefully, and I'm not explaining you what careful means, if you build this carefully and not necessarily optimally, but close to optimal way, I keep using the word optimal, although I don't quite like using the word optimal because optimality is not really well defined in this problem. If your data structure, if your BVH is good, then your ray tracer will perform very few ray triangle intersections in the end. Very few. How many? About, on average, it will perform only a handful of ray triangle intersections. Yeah, that's true. So I have millions and millions of triangles, and I'm going to be testing, let's say, 4 of them before I find the hit. Because when you think about it, in a scene, I have a ray that hits an object. That object, the ray will hit just one of its triangles, right? A ray will not hit all of the triangles of an object. It's going to hit one triangle, maybe 2 triangles, maybe 1 triangle on the backside as well. But if you traverse the structure in a careful manner, you can find the closest one. You can immediately find the closest one, or you can find the closest one earlier than the other ones. By first building it carefully and then traversing it carefully, you can avoid the extra unnecessary cost of looking at all the other triangles, which will return false when you try to do intersection test. So you can skip all that. You can only look at triangles that have a high possibility of intersecting with the ray. And there are not that many triangles that will have high probability of intersecting with a given ray. And if you build your data structure carefully, you can avoid all that computation. But to be able to do that, you're going to have to do a whole bunch of ray box intersections, right? If I'm only doing a handful of ray triangle intersections, that means I'm doing a whole bunch of ray box intersections. Yeah, so that's the cost. But I am building a hierarchy here. So this becomes a logarithmic search problem, right? So in logarithmic time, you can find the triangles that can possibly intersect with a ray. So the whole complexity of ray tracing can be reduced significantly using this. How do you build this? That's a whole topic of its own, and I am not planning to get into this. Yeah, there are different strategies for building this tree. You can build it from bottom up or top down. There are different strategies. But there are methods that, especially for BBHs, today we can build them very, very fast. And we can maybe not get the best possible BBH, but we get a reasonably high quality BBH, but we can build them super fast. That building a higher quality BBH that would give you better performance is not worth it, because it will take a longer time to build that higher quality BBH. As I said, it's a big topic, and that's why I'm not getting into the details of that. All right, so this is where I'm going to end this conversation. As I said, there are different data structures. Actually, last year, my students and I proposed an alternative data structure to BBHs that performs faster than BBHs, also takes up less memory. And this year we talked about how to implement this in hardware, so it really outperforms any kind of BBH. So there's still research going on in this topic, is what I'm trying to tell you. And there are different data structures that are not necessarily BBHs, but BBHs are today the most popular data structures used for accelerating ray tracing. All right, that's where I'm ending this conversation. But don't worry about the project. We're not going to be implementing a BBH. We're not going to have that many spheres to render, so don't worry about it. All right. Let's move on to our next topic, which is going to be GPU ray tracing with hardware acceleration. This is not going to be acceleration structure. This is hardware acceleration. It's a topic that I thought that I must at least mention. That in today's GPUs, today's modern GPUs, we have hardware units that are designed for ray tracing. Even though this GPU, by and large, is designed for rasterization, there exist hardware units. NVIDIA calls them RT cores, ray tracing cores, that are designed for doing ray tracing specifically. So we talked about the rasterization pipeline on the GPU. We said we had a vertex shader, and the output of that goes to a rasterizer, and the rasterizer calls our fragment shader. So we have programmable vertex shader and programmable fragment shader, and in between we have this hardware unit that does the rasterization for us, right? And this entire pipeline is run by the GPU hardware. So with this modern GPUs, we also have hardware ray tracing support. So that creates a bit of a more complicated pipeline for ray tracing. There's a ray generation shader that is a programmable shader stage that you write the code that generates the rays, and that's sent to an acceleration structure traversal that is going to be a BBH. It's going to be traversing the BBH sort of automatically, and then it's going to send possible intersection tests to our intersection shader, any hit shader for handling semi-transparent objects. And if it doesn't find any hit, it's going to call this miss shader. If it finds a hit, it's going to call this closest hit shader. So this pipeline is quite a bit more complicated, but that's what is needed for doing ray tracing. Less like a pipeline, more like a washing machine. Okay. Yeah, it is more complicated, because like over here with rasterization, we just feed in our triangles and they come in from one end and our pixels come out the other end. Here with ray tracing, we want to use ray tracing for doing all sorts of different things, not just for handling the primary visibility. Like we're going to be using it, next time we're going to talk about it, we're going to be using it for computing shadows, we're going to be using it for computing reflections. For all that stuff, we need this more flexible pipeline that can actually do other things that this rasterization pipeline won't be able to do, right? That's why it's a more complicated machinery here. But I am not planning to cover this topic in detail in this course. This is where I'm going to stop talking about it. I just had to mention that this exists. And if you guys are interested in that, please do check it out. But although it is not going to work on the current WebGL versions that are supported, but maybe in some future version of WebGL, we might have ray tracing support. Today, we do not have it. Only some graphics APIs support it. All right, so this is hardware accelerated ray tracing. But that's not the only way of implementing ray tracing on the GPU. We can implement a software that does ray tracing. And if you're writing a software, it's software, so you don't need hardware support for that to work, right? Because it is going to be software. And I want to briefly touch this, because this is exactly how we will be implementing ray tracing in our upcoming project. We're going to be implementing a software ray tracer on the GPU. And people have done this in the past a lot before we had ray tracing, hardware ray tracing support on the GPU. People still do that for all sorts of things. that's why I want to briefly touch on how something like this can be done. So here's the thing. With ray tracing, this is what I'm doing, right? I pick samples on the screen, I send rays that go through these samples, I trace them, I find intersections with triangles, maybe one triangle, maybe more, whatever intersections I find, and then I shade that point. And I do that for all of the pixel samples that I have so that I can form my image, right? That's the idea. But without hardware support, this is kind of hard to do. So how are we going to do that if we don't have hardware support for ray tracing, but we only have support for rasterization? How are we going to trick our GPU to do software ray tracing instead of rasterization? Here's how. Now, we're going to do rasterization, but we don't care about that rasterization. All we want is, I want some shader to run for each pixel. Basically, for each pixel on my screen, I want to run a shader, and inside my shader, I'm going to have a software implementation of ray tracing. Okay? So here's what I do. I just draw a quad on the screen, and I render this quad using rasterization. And that quad is just large enough to cover the entire screen. Okay? So when I do that, and I rasterize a quad, it's going to have very few vertices, right? And when I rasterize it, my rasterizer is going to call my fragment shader as many times as I have pixels. Now, I can do whatever it is that I want inside this fragment shader, right? I can do whatever I want inside that fragment shader. And it is inside this fragment shader I will be implementing my ray tracer, right? So my ray tracer is going to run inside this fragment shader. The project is implemented such that this vertex shader, with the help of interpolation and rasterization, will generate the primary rays for us. So once we get the fragment shader is going to have a ray. A ray that corresponds to the corresponding pixel. And then we run our software ray tracer inside this fragment shader, and that's going to render our final image that, let's say, it looks like this, right? So this is how we're going to be implementing ray tracing on the GPU. So in that case, I use my rasterization pipeline, but I didn't use it for anything useful. I just used it for rendering a screen size quad, right? I could actually make use of the rasterization pipeline, and I can handle the primary visibility using rasterization. So if I have these two triangles in my scene, I can render those two triangles using rasterization. And then I'm going to get the pixels that correspond to those triangles on the screen. And that's where I'm going to have my fragment shader. And inside my fragment shader, I can run my ray tracer. So if I do that, it's going to be more like this. Like, so this is full ray tracing. Like, I generate primary rays, and then I generate secondary rays for reflections, refractions, global illumination, whatever. If I use rasterization, then I'm going to be handling my primary visibility using rasterization. So I don't need that primary ray. And I can start my ray tracing exactly at this point, right? I can start my ray tracing at this point, which is where my fragment shader will be called, and I can run my ray tracer inside my fragment shader to all the secondary effects, to handle the secondary effects like reflections, refractions, shadows, and so forth. So in the upcoming project about ray tracing, we're going to have two rendering modes. One of them is going to just render a screen size quad and render everything using ray tracing. The other one is going to handle primary visibility using rasterization, and the secondary effects like reflections and shadows will be handled using ray tracing. All right. So that's where I'm going to stop for today. Next time around, I want to spend some time and talk about how we can handle shadows and reflections using ray tracing. So that's going to be our next topic. That being said, I think you can start looking into our next project and start implementing the next project right away before waiting for our discussion on shadows and reflections. Well, at least the parts, the primary visibility part, you can implement. The rest is going to be relatively simple anyway. So most of the information that you need for implementing our next project, we've already talked about. All right, but this is where I'm going to stop today. Thank you, and take a look at the project. I hope you're going to enjoy it. I certainly enjoyed it. Good luck with that, and I'll talk to you next time.